Hey, so we're going to touch on acids and bases next, and what we're going to look at is two different types of evidences that you need to know when you classify acids and bases. So we have what's called empirical evidences, and these are evidences that can be sensed with any one of our five senses. So sometimes sense of taste or smell or touch or whatever. These are physical evidences that we can observe. And then we've got what's called theoretical evidences, and these are basically just evidences that we think exist. So we have a pretty good idea of what an acid and a base is really composed of, but because we've never actually seen those components, it's hard for us to say definitively, and in science we just refrain from doing that, saying that we know something when we haven't seen it. And so we leave that under the theoretical bar there where we have to classify things. So if we take a look at empirical evidences, these are a lot of evidences that we went through in junior high science when we talked about acids and bases in grade 9. So some of this might be a little bit of a review, but acids taste sour, so things like lemon juice have that sour taste. That's a property of acids. We know that its pH is less than 7. This is something that we can measure, and so it's an empirical evidence. We know that acids contain ions in solution because they'll conduct electricity, so that's why we call them an electrolyte. And then we know that if we do a litmus test on acids, that it'll turn the litmus paper red. For bases, they're slippery, bitter, pH is greater than 7. Again, they are electrolytes. They do have ions in solution, and then they turn litmus paper blue. So these are all evidences that we can observe, see, touch, smell, or whatever with our five senses, and we can classify acids and bases that way. We can also classify bases using theories that we've devised, and the theory really that we've devised is pretty simple. We say that acids contain H+, and we say that bases contain OH-. And so we'll explore this a little bit more. We'll explore a little bit about how these theoretical evidences are tied to some of the empirical evidences, specifically the pH scale and the pOH scale. And so in the next clip, that's what I'm going to have up on here on the board, is just those scales and how they're related, these empirical evidences to the theoretical evidences. So we'll be right back. Okay, everybody, so we're back with an explanation about the pH and pOH scales. And this diagram here I know looks kind of big and a little bit intimidating, but just follow along with me as I go through the description of the diagram so that you don't get lost with all the different things that are on here. And if we go step by step, it should make perfect sense. So the first scale that we're going to talk about is the one that you're most familiar with, which is the pH scale. Now pH, you may want to write this down in your notes, stands for power of hydrogen. So in the previous clip, I talked about how our theoretical evidence for acids is that acids contain H+. And so naturally, the more H+ is in a solution, the more acidic a solution is going to be. So if we want to measure the power that hydrogen has, that's going to dictate to us then how strong or how weak a particular acid is going to be. And so the pH scale is an infinite scale. It doesn't have two ends like some scales do. Most of the acids and other solutions that we find that sit on the pH scale, most of them sit between 0 and 14. So normally you see a pH scale that's listed from 0 to 14, but we can have pH numbers that are greater than 14, and we can also have pH numbers that are negative, less than 0. That is possible. And you may see that with some of the calculations that you might do where you would see some of those numbers reach outside these boundaries every once in a while, not very often. So this power of hydrogen is what we're really trying to measure when we're placing a solution on the pH scale. If we place it, or if it's placed, we do a pH measurement of a particular solution and it's found to have a pH of 2.5, that gives us an indication of what or how much hydrogen is found in that solution. Conversely, a new scale that you may be familiar with, or it may be brand new to you, is this scale of pOH. Now pOH, just like pH, measures the power, but it doesn't measure the power of hydrogen, it measures the power of hydroxide. Thus why we call the scale pOH. And so if you remember from the previous clip, bases, their theoretical evidence is that they contain OH minus in their solution. And so the more OH minus that's in the solution, the stronger the base is going to be. Now you'll notice something about this scale. This is kind of written backwards in relation to the pOH scale. And the reason that I've done this is because everything from 7 over is considered acids, and everything from 7 over this direction to the right are considered bases. And right here in the middle is what we consider to be a neutral pH or pOH. So it's a substance that's neither an acid nor a base. The acidic properties and the basic properties have basically neutralized each other out, and so there's no acidity or basicity to those solutions. Now, the interesting thing that's different from many other types of scales, like a temperature scale, or let's say the Richter scale, where you go from 0 to 10. On a Richter scale, an earthquake of 1 is really weak, and an earthquake of 10 is very devastating. On the pH scale, we don't go from, say, strongest acids to weakest acids over there necessarily. What you can see up here at the top that I've labeled is right here at neutral. Just on this side of neutral, we have the weakest acids. And then the acid strength increases as we move out to the peripheral area of the scale. Bases are the same way in the opposite direction. The weakest bases are close here to neutral, and the strongest bases are furthest away from neutral. And so it's a slightly different setup where many scales go small to big this way. The pH scale starts kind of in the middle of the scale, neutral, and then we get stronger as we move out to the edges of that scale. And so you can see I've labeled this on here. Everything that has a pH of less than 7 is considered an acid, but the further away from 7 we are, the stronger the acid is. Conversely, for bases have a pH of greater than 7, and the further away from 7 that we are, the stronger the base is going to be. So that's the pH scale. The pOH scale, you can see, is flipped, as I've mentioned. And all this is measuring is the power of hydroxide. So naturally, it would make sense that if I have something that has a pH of 7, it's going to have the same amount of H plus as it does OH minus. That's what causes it to be neutral. And if you look at H plus an OH minus, that really just makes HOH, which is water, which is a neutral substance. But this is where we move into this next sort of level here on these scales. And these two scales are what we call a logarithmic scale. Now, you may be familiar with logs, you may not be. If you're not, that's okay. All you really need to know about these scales is that anytime that I move one tick on the scale, it's actually 10 times smaller or greater, depending on which direction I'm moving. So if I'm moving in this direction, I'm becoming a stronger acid, which means if I go from 4 to 3, an acid that has a pH of 3 is 10 times more acidic than an acid with a pH of 4. And that's because the further we move away from 7, the stronger the acid becomes. So you kind of might say to yourself, well, that's kind of strange. Why then do we have a scale where the smaller number is the stronger solution? And the way that this is explained is that the pH scale, when we convert it into concentrations, so a concentration of H plus, measured in moles per liter, okay, these numbers are actually on base 10 with a negative exponent. So you can see that the largest number in this line from 0 to 14 is actually 10 to 0 because it's 10 to the 0, and then the next concentration is 10 to the negative 1. This concentration here is smaller than this concentration. If you plug this into your calculator, this is going to be 1, and this would be moles per liter. 10 to the power of 0 is 1, and so this would be 1 moles per liter. This here, 10 to the negative 1, would be 0.1 moles per liter, which is 10 times less acidic than 10 to the 0. And so this is why a pH of 1 is 10 times less acidic than a pH of 0, is because the concentrations are expressed in this way. And so clearly you can see that as I go along the pH scale, you can see that the solution that has a pH of 12 is going to have a hydrogen ion concentration of 10 to the negative 12, which is a really, really small number, moles per liter. And so that's how pH is related to the hydrogen ion concentration. pOH has the same relation, but now with hydroxide ion concentrations. And so again, same concept. If I've got a solution that has a pOH of 3, compare it to another solution that has a pOH of 2, well, this solution here is going to be 10 times more basic than this solution here, because the concentration of those two solutions, you can see this concentration is a larger concentration in moles per liter than this one by a factor of 10. And so if you keep that in mind when you're asked questions like, how many more times acidic is a solution of pOH, how many more times basic is a solution of pOH2 compared to pOH5? Well, this is 1, 2, 3 ticks on the scale, so 10, 100, 1,000 times more acidic. pOH2 is 1,000 times more acidic than a solution with a pOH. I keep saying acidic. 1,000 times more basic than a solution with a pOH of 5. So we can actually represent this with a little bit of a diagram, and that's what this diagram is down here along the bottom. If you take a look at neutral substances, again, this is showing just the size of how I've written the symbol dictates or represents how much of that ion is in the solution. So if I look at a neutral substance, for example, the size of these are basically the same. And so I got the same amount of H plus as I do OH minus, and that therefore represents a neutral substance. For acids, I have way more H plus in the solution than I do OH minus. You can see that for a really strong acid, I'll have hydrogen ion concentration of 10 to the 0, or in other words, 1 mole per liter. And for hydroxide ion concentrations at that same pH, you can see that the concentration of hydroxide ions is 10 to the minus 14. It's a really, really small number. And so acid properties dominate this side of the scale because there's way more hydrogen ions in those solutions than there are hydroxide ions. And then you can see as I move over to the base side of the scale over here on this side of 7, I now am starting to get way more hydroxide ions in solution compared to the hydrogen ions. And way over here you can see this is why the base properties dominate these types of solutions, is because they contain way more hydroxide ions than they do hydrogen ions. And so this scale is actually equal vertically, all right? And so what we end up having here is we say, if I have a solution that has pH of 3, then that means that the solution also has a pOH of 11. Now, these two solutions, this one solution is the same solution, but we can describe it as having a pH of 3, or we can describe it as having a pOH of 11. And this is going to tell us two different things. It's going to tell us that the hydrogen ion concentration is 10 to the negative 3, and it's going to tell us that the hydroxide ion concentration is 10 to the negative 11 moles per liter. And so you can do this for any solution that sits on this scale. Because I know that the solution has a pH of 3, I know that this is going to be an acid. Any substances that have a pOH greater than 7, those are also going to be considered acids. So all of the acids have these properties here, and all of the bases have these properties here. And what we can do is we can actually get some formulas out of this. So I'm going to write some formulas over here on this side. And these formulas, you need to be able to understand what they mean and be able to use them. So the first formula that we get here is, if you look at each of these, 11 plus 3, 10 plus 4, 9 plus 5, 8 plus 6, 7 plus 7, all of these mathematical calculations, they all equal 14. So our formula here is the pH plus the pOH of the same solution will always equal 14. And so you could be asked questions like, if the pH of a solution is 2, what would be the pOH of that same solution? And you could use that formula to calculate that, just by going 14 minus the pH, do a little bit of algebra there. The next formula that we get is if I have the pH of a particular substance, I can calculate what the hydrogen ion is going to be. And so the hydrogen ion concentration in moles per liter is what I can calculate. So the hydrogen ion concentration is equal to, and then if I take a look at this, this is just on base 10, and it's to the negative whatever the pH is. So if my pH is 1, and I want to calculate what the hydrogen ion concentration is, then I just take my pH value and I put it on base 10 as a negative exponent. So 10 to the negative 1. If my pH is 3.45, okay, then my hydrogen ion concentration would be 10 to the negative pH. In other words, 10 to the negative 3.45. So that's our formula here, is the hydrogen ion concentration is just 10 to the negative pH. The next formula that we can get from this is very similar. It's just calculating the hydroxide ion concentration. So that's simple. The one thing that you have to be careful of with this is you have to remember that if you want the hydroxide ion concentration, you must use the pOH value for that solution. If you go 10 to the negative pH, it is not going to give you the hydroxide ion concentration. It's going to give you the hydrogen ion concentration. So if you're asked a question of, okay, we've got a solution of a pH, a solution that has a pH of 3.45. What is the hydroxide ion concentration? Lots of kids will make this mistake. They'll just go, oh, okay, I know how to do this. I'll go 10 to the negative 3.45 and hit enter on my calculator, and that's the number. And that's not the right answer. The right answer is if you're looking for the hydroxide ion concentration, I have to first convert this number into a pOH value and then go 10 to the negative pOH in order to get my hydroxide ion concentration. And so that's why these formulas are written like that. So pay attention to how those formulas are and what is required in order to calculate those things. Now, just like in mathematics, there's always an opposite to what you can do. So if you're multiplying something, to undo that multiplication, we divide. In math, if you do an addition, to undo that addition, we subtract. Now, in math, when we're doing stuff on base 10, if I'm doing a calculation on with exponents on base 10, I can undo that base 10 calculation by using a button on my calculator called log. And so if, for example, I want to calculate the pH of a solution by using the hydrogen ion concentration, then to undo or to reverse this calculation, or to kind of go backwards, I would take the negative log of that substance. So the formula is going to look like this. So if you're given what the hydrogen ion concentration is for a particular solution, you can calculate the pH of that by going negative log of that number in your calculator. And so you can try a few of those. We'll do a couple practice questions just so you can kind of get a sense and a feel for how some of these formulas are supposed to work. But these are the five pH and pOH formulas that you need to know. We'll be right back with a couple of examples. Okay, so here's a couple of examples that we're going to do as it relates to calculating pH and pOH and using those numbers to either calculate concentrations or using concentrations to calculate pH and pOHs. This is a concept that's needed for both Chem 20 and Chem 30. This SIGDIGG rule here more applies to Chem 20. In Chem 30, we're really not worried as much about significant digits for some strange reason. I'm not totally sure, but I will explain this rule so that everybody's got it, but just keep that in mind as to what class you're part of, either Chem 20 or Chem 30. So here's the special SIGDIGG rule that you need to know when calculating pH and pOH, especially in Chem 20, and it's this. I've got this statement here, and I would write this statement down in your notes. And whatever number goes in this blank must go in this blank, and that's how you can figure out how you need to do the rounding of your numbers. So if you have a pH or a pOH that's given to you in the question that has X decimal places. So let's say for the purposes of this example, it has 3 decimal places, okay? Then the concentration must have, and then whatever number goes in here must go in this blank, 3, but not decimal places, it must have 3 SIGDIGGs. And with some of the examples that I'm going to do on the board, you can see where number of decimal places and number of SIGDIGGs sometimes differ from each other. But this number must remain consistent. So if your pH and pOH has 3 decimal places, then your concentration must have 3 SIGDIGGs. The backwards is also true. If you're given a concentration in the question and it's got 3 SIGDIGs, then your pH and pOH that you're going to calculate from that must have 3 decimal places. And so if this number's a 2, then this number's got to be a 2. If this number's a 4, then this number has to be a 4. The thing that kids get most confused by is they'll either go SIGDIGs to SIGDIGs or decimal places to decimal places, or probably the most common mistake is kids will think that the pH, pOH is number of SIGDIGs and the concentrations is number of decimal places. So it's just something you got to memorize. You got to spend some time just knowing this SIGDIGG rule when we're talking about rounding for these answers. I've got a couple of examples to illustrate what exactly this means and how we're supposed to use this. So if you take a look at this first one right here, it's a very simple calculation where we're given pH of 4.65 for a particular solution. And the question is just simply asking, what's the H plus concentration for this solution? So anytime that you're asked to calculate something, come over here to your list of formulas and just identify what it is that you're being asked to calculate. And for this question, I'm being asked to calculate H plus. So I'm going to find the formula that says H plus is equal to and use that one. And so this is the concentration of H plus is equal to 10 to the negative pH. So you can see I've written that here, and then I've plugged in what my pH is, 4.65, but remember that it's got to be 10 to the negative 4.65. And then I just plug that into my calculator. Make sure that you use the second function in your calculator and then hit the log button. That will give you the 10 to the exponent that you want to use. And if you plug all this in correctly, you should get 2.2 times 10 to the negative 5. And because this is a concentration, my number is going to punch out with units of moles per liter. And so that's all you got to do for those types of questions. Pretty simple. You're given a pH, calculate the H plus ion concentration. That's all you gotta know. If you're given a pOH value, then you can calculate the OH minus concentration directly using those formulas. So just pay attention to what the question's asking. Second example is, let's say that we're given the concentration of an acid. So the acid has this concentration, but I don't know yet what the hydrogen ion concentration is. Notice that the concentration of HI is different than the concentration of H plus. Okay, they're not always the same thing. Now, sometimes they can be the same thing, and as you'll notice here in this question, it turns out that they are the same concentration, but sometimes they aren't, and so you've got to pay attention to this. And the way that we figure out whether they're the same or not the same is I have to write out an ionization equation. So if I have HI as my acid, I know that this acid is going to ionize. So I write out an ionization equation. It's going to ionize into H plus and I minus. Now, for this concentration right here, this is the concentration that was given to me in the question, which is 6.57 times 10 to the negative 2 moles per liter. Now I know that 1 mole of HI is going to give me 1 mole of H plus. So if this is how many moles I have in 1 liter, then this is how many moles of this substance I'm going to have in 1 liter, because one of these makes one of these. And so the concentration of HI turns out to be the same as H+. Now if I had a different acid where I had 1 mole of this acid makes 2 moles of H+, well then I would need to double that concentration in order to calculate properly what the H+ concentration would be. In this example, I don't have to do that. It's the same because the ratio is 1 to 1. So now looking at this, I have my H+ ion concentration. It's right here, 6.57 times 10 to the negative 2 moles per liter. Now, what can I calculate from that? Well, if that's the number I have, I want to look for a formula that has H+ ion concentration in it. And so this formula right here is the formula that has H+ ion in the actual formula. So that's the formula I'm going to want to use. But note that if I take the negative log of the H+ ion concentration, that's going to give me the pH. Now the question is asking for not the pH, but the pOH. In order to get to the pOH though, I have to calculate the pH first. So I go ahead and do that. My pH is equal to a negative log of the H+ ion concentration. I plug those numbers in, negative log of this number. Make sure that when you're doing these numbers in your calculator that again you're using the EE button on your calculator so that you're properly calculating scientific notation without causing yourself any grief and getting wrong answers that way. Do that in your calculator, you should end up with 1.182. Now, the reason my answer is like this is because if I go back up here to my SIGDIGG rule, my concentration had 3 SIGDIGGs, which means that my pH or pOH value, in this case pH, has to have 3 decimal places. So 1.182 is going to be my answer for that. But remember, I don't round until the very end. So actually this number is a bigger, longer number in my calculator. And I want to calculate the pOH. So to calculate the pOH, I'm going to use this formula really easily. Just 14 minus the pH is going to give me my pOH value. So I plug that in and I get a pOH value of 12.818. Notice that that is still written to 3 decimal places because my pH and pOH value must have 3 decimal places when my concentration has 3 SIGDIGs. And so, yes, this pOH value does have 5 significant digits, but this is the rounding rule for significant digits when dealing with pH and pOH values. And so that's what we have to follow. This number has 3 decimal places. That's why I write that many digits for it. And that's it, guys. Those are the 2 examples that you really need, I think, to get started.